In our last lecture, we described AI as a model that maps inputs to outputs, where outputs are a solution to an information processing problem. In this lecture, I'm going to give you examples of inputs from a variety of domains that we might feed into an AI, and also example model outputs, which are solutions to specific information processing problems that we could ask the AI to solve. I'm also going to talk about feature representations. I'll expand on what we talked about in the first lecture, which is that deep learning models are unique from other types of machine learning in their ability to find appropriate feature representations for the data. Finding relevant features is so important for solving problems in high-dimensional domains, which is the case for domains key to our everyday life, like vision, sound, and language. I'll discuss what it means to have an efficient feature representation and why this is needed, and also relate this to the function of the biological neural networks in our brains. But first, before discussing the representations that our neural networks can extract from data, let's talk about how we might represent the data that we feed into the neural network. Let's say we want our model to tell us something about images. If we had black and white images, our representation might be the intensity values of each pixel. If it's an 8x8 image, like the square on the left, then we'd represent a single piece of data as 64 numbers, where each number corresponded to the intensity value for a pixel. For a 30x30 image, we'd have 900 values, and then for a 150x150 image, we'd have 22,500 values. You can see that the number of values will grow very quickly. Now, if we had color images, we need to represent for each pixel the red, green, and blue intensity values, so we'd have 3 times the number of values that we needed for the black and white images. So what are some information processing problems that we can have our model solve about images? Well, we could have it predict what time of day a picture was taken and ask the model to output either morning, afternoon, or evening. This would be like a classification problem. Or we could require the model to be more precise and have it predict exactly what time of day the picture was taken to the minute. We could also have a model predict whether this would be a popular picture on an Instagram and have it output a yes or a no. Or we could have a model predict a popularity rating for the image between 1 and 10. We could ask the model for specific visual concepts, such as tell us where the top of the mountain range is. And here, the model might produce a sequence of zeros and ones, where the ones would correspond to the pixels that contain the top of the mountain range. Now let's look at sound. We can represent sound as a sound pressure waveform, and this would be a sequence of decibel values over time. Alternatively, we can also represent sound as a spectrogram, and here the waveform is decomposed into the amount of sound that is present in each frequency over different units of time. So what are some information processing problems that we can ask models to solve about sound? Well, we can use it for speaker identification and ask, is it the owner of the account that's speaking right now? We can use it for speech recognition and ask what words were being uttered. We can do sound recognition and have a model predict what animal made that sound. And there are many, many more possibilities. Now let's look at language text. There are many ways to represent text. One basic way is to represent text with how often different words occur in a piece of text. And this is also known as a bag of words model because we're not keeping track of the order of the words, and so it's like we're shoving all the words into a bag. So here we see 2 pieces of text, and on the left is a bag of words representation for how often different words occur in each of the 2 texts. So we see for text 1, the word 12 occurred 0 times, the word 30 occurs 0 times, the word treasuries occurs once, the word US occurs once, and so on. And then for text 2, the word 12 occurred once, the word 30 occurred once, the word treasuries occurred once, the word US occurred once, and so on. Remember that all our input always needs to be represented in a way to the model that can allow for computational processing. So this means that the data needs to be translated into a numerical representation. Here, with the bag of words, we would represent a piece of text as a sequence of numbers that corresponds to the number of times that word occurred in that text. In practice, we'd have many types of preprocessing that we could do on a piece of text. For example, we might collapse all numbers that occur in the text and use it as a single word token. We might remove all common stop words like the, and, an, etc. We might reduce all the words to their base forms, like reduce the word running to run. And there are many more things we could do. The bag of words here that I show is just one of many, many ways of representing language data. And there are many other ways, such as representing words as vectors, where we can capture similarity between different words, and also other ways where we might preserve the information about the sequence of words that occur in a sentence, etc. Now, what solutions could AI provide about a piece of text? Well, we can ask, if this piece of text were published as a news article, will the stock market rise? We can also ask what percentage the stock market will change. We can ask, if this piece of text were to appear online in a news article, how many views will it attract? So we've gone over examples of defining inputs and how we might represent these inputs in a form that a computer can understand, and also how to define some outputs, which are the solutions we want our AI to answer. We went over such a small subset of the possible inputs and outputs that an AI can have, but I wanted you to get a flavor for what it's like to be very specific about defining these inputs and outputs.